Mastering algorithm design for real-world performance in today's fast-paced world. Efficient algorithm design isn't just about solving problems, it's about crafting scalable solutions that adapt to evolving challenges. Whether you're optimizing code for machine learning models or designing routing systems for global logistics networks, your choice of algorithms defines success. The difference between a sluggish application and a blazing fast one often hinges on subtle decisions during the design phase. By understanding core principles and modern techniques, developers can build robust systems that thrive under pressure. The foundation of effective algorithm design at its heart, algorithm design involves transforming abstract problems into concrete computational processes. This requires identifying patterns, defining constraints, and selecting the right tools for the job. A well-designed algorithm balances simplicity, efficiency, and extensibility. Mastery begins with recognizing that no single approach works universally. Greedy algorithms excel at local optimizations, while divide-and-conquer strategies break complex issues into manageable fragments. Understanding when and how to apply each technique is crucial. Clarity. Code should reflect the logic behind the solution clearly. Ambiguity leads to errors and maintenance nightmares. Efficiency. Prioritize runtime and memory usage, especially when dealing with large-scale data processing. Analyzing time and space complexity. A foundational skill in algorithm design is evaluating time and space complexity using Big O notation. While asymptotic analysis provides theoretical bounds, real-world applications demand empirical validation alongside theoretical models. Consider sorting algorithms as a prime example. Quicksort offers average case $O, n\log n, dollar performance, but worst-case scenarios degrade to $O, n squared, dollar. Awareness of these nuances guides better decision-making under uncertainty. Beyond worst case, practical performance metrics. While academic analyses emphasize worst-case behavior, professionals often prioritize amortized complexity and constant factors. Techniques like memoization reduce redundant computations, improving actual execution times even if Big O remains unchanged. Data locality plays a significant role too. Accessing contiguous memory blocks, as in array-based structures, can drastically outperform linked lists in cache-friendly environments, highlighting the importance of hardware-aware design. Design patterns for common problem types. Certain problem types recur frequently in software engineering, demanding specialized approaches. Dynamic programming shines for optimization problems with overlapping subproblems, whereas graph traversal algorithms handle connectivity issues elegantly. For instance, finding the shortest path in a weighted network employs Dijkstra's algorithm, a classic demonstration of how graph representation choices, adjacency matrices versus lists, impact implementational feasibility and speed. Dynamic programming stores intermediate results to avoid recomputation, ideal for tasks like string matching or financial modeling. Backtracking systematically explores potential solutions while pruning unpromising branches early, commonly used in constraint satisfaction puzzles. Optimizing recursive algorithms. Recursion simplifies many algorithm implementations, particularly for problems exhibiting recursive substructure. However, naive recursive approaches risk exponential time complexities and stack overflow vulnerabilities. Tail recursion optimization mitigates some overhead by allowing compilers/interpreters to reuse stack frames. Languages supporting this feature, like Erlang or Haskell, enable writing elegant yet performant solutions. Iterative versus recursive trade-offs. Converting recursive functions into iterative versions reduces call stack pressure and eliminates risks associated with deep recursion. Stack simulation techniques replicate recursive control flows manually, preserving functionality while enhancing stability. However, iteration sometimes sacrifices elegance for safety. Careful profiling determines whether the benefits of reduced overhead outweigh loss of natural expressiveness in particular contexts. Heuristics and approximation strategies. Intractable problems requiring exact solutions face NP hardness barriers. Here, Heuristic methods offer viable alternatives that provide good enough answers within reasonable computation limits. Genetic algorithms mimic biological evolution through mutation, crossover, and selection mechanisms. They excel in search spaces where traditional gradient descent methods fail, though convergence guarantees remain elusive. Simulated annealing mimics metallurgical cooling processes to escape local minima traps systematically. Taboo search uses memory structures to prevent revisiting previously explored states, guiding searches toward promising regions. Probabilistic approaches for uncertainty handling real-world applications increasingly deal with uncertain inputs, from noisy sensor readings to incomplete databases. Probabilistic algorithms incorporate statistical distributions rather than deterministic assumptions. Monte Carlo simulations leverage randomness to estimate probabilities numerically. Their power lies in approximating difficult-to-calculate quantities through repeated sampling, albeit with inherent variance in outputs. Risk management through confidence intervals to manage output variability. Probabilists employ confidence intervals that quantify estimation accuracy. Tighter intervals require more samples but yield higher reliability in decision-making contexts. Bayesian inference updates prior beliefs with observed evidence iteratively, creating adaptive models that learn continuously from incoming data streams. This makes them invaluable for machine learning and predictive analytics systems. Distributed computing and parallel processing. Modern architectures demand algorithms capable of harnessing multi-core processors and distributed clusters effectively. Designing such algorithms necessitates careful synchronization mechanisms and communication protocols. MapReduce frameworks exemplify this paradigm by decomposing tasks into mappable units processed independently before reducing results globally. Proper partitioning ensures load balancing across computing nodes. Pipeline architecture, overlapping stages of different operations increase throughput by minimizing idle time between dependent tasks. Load balancing, dynamically redistributing workloads prevents bottlenecks caused by uneven distribution among parallel threads/processes. Error resilience and fault tolerance mechanisms. Robust algorithm designs anticipate failures and incorporate recovery mechanisms automatically. Checkpointing allows restarting computation from saved state snapshots instead of rerunning everything from scratch. Consensus protocols like Paxos or Raft ensure agreement among distributed components despite message losses or node crashes. These form the backbone of reliable cloud services managing massive scale-outs daily. Circuit switching versus packet switching paradigms. Communication network algorithms differ fundamentally based on underlying infrastructure. Circuit-switched systems guarantee bandwidth allocations upfront, while packet-switched models dynamically route discrete packets through available paths. This distinction influences quality of service, QoS, policies implemented via queuing theories. Priority scheduling algorithms optimize latency-sensitive traffic delivery against bulk transfers competing for same resources. Ethical considerations in algorithmic development. As artificial intelligence becomes ubiquitous, algorithm designers bear responsibility for unintended consequences their creations might produce. Bias embedded in training data can perpetuate discrimination unless actively mitigated through fairness-aware designs. Transparency measures, including explainable AI techniques, help demystify black box models' internal workings. Auditable logs tracking input-output relationships enhance accountability when decisions carry legal implications. Fairness constraints. Incorporating demographic parity checks detects disproportionate impacts disproportionately affecting certain groups. Privacy preservation. Differential privacy adds noise to query responses, protecting individual identities while retaining aggregate insights useful for analysis purposes. Testing and validation methodologies. Rigorous testing verifies whether designed algorithms meet specifications accurately. Unit tests confirm basic functionalities, while integration tests validate interactions with external dependencies properly. Fuzz testing exposes edge cases through random input generation, uncovering hidden flaws that static verification alone misses easily. It forces engineers to consider unusual situations beyond typical test suites cover normally. Formal verification techniques. Mathematical proofs establish algorithm correctness formally. Poor logic specifies preconditions/post conditions, precisely enabling formal verification procedures, ensuring programs behave correctly regardless of initial conditions. Model checking exhaustively examines finite state machines representing system behaviors against temporal properties expressing desired operational characteristics. Useful for verifying concurrent programs where race conditions pose significant threats otherwise. Performance optimization practices. Micro-optimizations tweak low-level details, improving instruction pipelines, cache utilization, or branch prediction accuracy minutely. These incremental improvements accumulate significantly under high-throughput scenarios. Leveraging vector instructions, SIMD, accelerates batch operations, performing identical computations simultaneously on data elements grouped together spatially contiguously stored in memories accessible quickly. Loop unrolling, manually expanding loop bodies, reduces overhead caused by repeated condition evaluations and increment/decrement operations inside loops. Branch prediction. Modern CPUs speculate ahead of time which paths program controls flow likely follow next, minimizing pipeline stalls resulting from mispredicted branches. Documentation and maintainability principles. Comprehensive documentation ensures long-term viability of algorithm implementations even when original authors leave projects unexpectedly. API references clarify function signatures while tutorials demonstrate idiomatic usages beneficially. Code comments explaining rationale behind non-obvious choices benefit both immediate teammates working collaboratively and future contributors inheriting legacy systems requiring modifications later. Version control history. Git commits record changes chronologically, providing audit trails showing evolutionary pathways taken during successive iterations of refinement process. Automated testing frameworks. CI/CD pipelines execute regression suites upon every commit, preventing regressions slipping unnoticed into production deployments accidentally. Future directions in algorithm innovation. Quantum computing promises exponential speedups for select problems suitable for quantum advantage exploitation. Shor's algorithm demonstrates factorization capabilities unfeasible classically currently, threatening existing cryptographic schemes. Near-sensor computing shifts processing closer to data sources, reducing transmission costs dramatically. Edge AI devices now run lightweight neural nets locally instead of offloading heavy lifting completely onto centralized clouds usually. Adaptive systems through machine learning. Reinforcement learning trains agents to discover optimal strategies, autonomously interacting with dynamic environments. Unlike conventional rule-based approaches needing explicit programming, this enables emergent behaviors arising naturally from reward maximization objectives defined exogenously. Federated learning decentralizes model training, keeping private data localized. Devices contribute parameter updates, anonymously aggregating collective knowledge, securely enhancing overall model quality without violating confidentiality agreements directly. Conclusion. Algorithm design transcends coding. It's an art form combining mathematical rigor with creative insight. From classical paradigms to cutting-edge innovations, mastery demands continuous learning and experimentation. Whether refining existing approaches or inventing novel solutions, always ask, how does this contribution advance our ability to solve meaningful problems better than previous generations could achieve? That question fuels progress, shaping tomorrow's technologies relentlessly.